In my last video, I introduced a structural attraction towards motivic complementarity across spacetime boundaries, a subtle life force operating at every scale binding the universe together. I then presented this equation, balancing cosmic particle count, gravity, and the speed of light, implying a light-matter duality in spacetime dynamics. Because motivic information multiplies the same way classical information adds together, that light-matter complementarity equation can be factored out into an infinite number of scales, revealing a structural complementarity between scales of matter and light hidden within the initial complementarity of all matter and all light. Given the mismatched units of that equation, we'll ignore it for now and focus purely on its mathematical structure, specifically how such an infinite product structure defining the duality of light and matter contains general relativity as its macroscopic coarse-grained limit. We start with the scale invariant constraint of complementarity between discrete matter-like structure and continuous light-like flow. At any resolution, harmony is expressed as a product of paired divergences equaling 1. You can keep subdividing terms into finer complementary pairs, adding more factors to the product, though no matter how deep you go, the product remains exactly 1. In continuous form, acquired by taking the log of both sides, we get a product integral over all scales, S. This implies the integral of the log of the divergence density over the entire hierarchy of scales is 0. That's the key. Total logarithmic mismatch across all scales is precisely 0. The universe remains self-consistent at every resolution. To get to classical spacetime, we have to consider coarse graining, looking at the largest scales up to some cutoff we will call S0. The tail, all the finer layers we ignore, contributes about 1. At small scales, the life force enforces near-perfect local complementarity. Each tiny term is almost 1 and their product converges to 1. So the coarse product approximates the full infinite product, meaning the effective constraint at macroscopic scales simplifies to a single balance condition. This effective divergence acts as the coarse-grained action functional, basically a value that tells us how much the large-scale universe is out of balance. In the classical regime, large scales and weak gravity, we expand this action functional in powers of small changes to the metric which describes the spacetime geometry. We write the metric as flat space plus a tiny deviation. That h term is a very small perturbation, a tiny warp in spacetime. Because h mu nu is small, we can expand the effective divergence as a Taylor series. The expansion looks like this. The constant term doesn't matter. The linear term vanishes because flat space is stable without matter. The quadratic term, the first real correction, turns out to be proportional to the curvature, giving us gravity. Higher powers are tiny for weak gravity, so we drop them. The quadratic term is directly proportional to the Ricci scalar r. The Ricci scalar is a single number calculated at every point in space-time, measuring how much the space is curved at that point. When we expand the coarse-grained action functional to second order and the metric perturbation h mu nu, this second order piece functions exactly like the curvature term in Einstein's theory. The matter term comes from how mass and energy affect the action when we vary the metric, the shape of space-time. This gives us the stress-energy tensor T mu nu, basically the density and flow of mass and energy in spacetime that tells spacetime how to curve. In our coarse-grained model, requiring the action to be stationary gives the equations that tell spacetime how to curve in response to mass and energy. This reproduces the Einstein field equations, where the left side, the Einstein tensor, measures curvature, and the right side, the stress-energy tensor, measures matter and energy content.